Now we come to the Copenhagen interpretation. The Copenhagen interpretation is the most popular and widely accepted interpretation in quantum mechanics today. By the late 1920s, a new theoretical basis for the physics involving atoms had been created. It's important to state that despite the promising nature of the Copenhagen interpretation itself, there laid several underlying problems. These problems would disturb even the most notable of minds, one famous example being Einstein himself. As an overview, a study of the Copenhagen interpretation begins with the famous scientist Niels Bohr. Bohr is known as one of the greatest minds of the 20th century, and his approach to solving problems within physics was adopted by many around him, although not all. Bohr worked from his institution in Copenhagen, developing quantum theory, and remained there until he fled Denmark in the face of Nazi invasion. But what does Bohr's interpretation entail? At the very heart of the Copenhagen interpretation is the distinction between the microscopic, which display the behaviour that we associate with quantum mechanics, and the macroscopic. What's more is the interpretation expresses a degree of futility, in the sense that it's pointless to describe properties of an isolated quantum system. In other words, the only information we can gather from such a system comes through measurement. This approach to quantum mechanics did not please all, especially the likes of Einstein, who believed that the interpretation was incomplete and was therefore determined to prove inconsistency in the theory itself. This whole notion of measurement is fundamental to Bohr's interpretation. As such, it would be wise to look at an example of measurement in a more scientific fashion. We've already looked at one example, where a measurement was made on a quantum system in the example of a single photon passing through a double slit. According to Bohr's interpretation, before a measurement is made, the photon exists in a superposition of states. It's meaningless to try and define the state of the particle at this point, however, and indeed, we cannot even if we wanted to. However, once a measurement of an observable or physical quantity is made, the wave function associated with the photon is said to collapse. An important key feature of the Copenhagen interpretation is the notion of indeterminacy. Indeed, while some, like Einstein, used this to point to the belief that the theory was complete, Bohr seemed to be happy with this principle. One factor and one important part of Bohr's interpretation is the famous correspondence principle. Key feature of the Copenhagen interpretation, developed at the outset of Bohr's endeavour to create a complete quantum theory, is the correspondence principle. The principle uses the idea of a classical limit. This is seen in the Planck limit distribution, which becomes equivalent to the Rayleigh distribution for low frequencies. Bohr realised that for hydrogen atoms, the energy levels become closer and closer for higher n, the principal quantum number, and he thus decided that this meant that the higher energy values corresponded to a classical region. At this point, regarding the correspondence principle, it's possible to look at Bohr's famous restriction of angular momentum. Bohr realised that the angular momentum of an atom is quantized. Considering a simplified model of the atom, this can be shown quite easily. Here, we consider the electron to be a standing wave. We then note that the standing wave will have nodes and be an integral number of wavelengths. This leaves us with the fact that 2 pi r can be said to be equal to n lambda. We know from the de Broglie wavelength that lambda is equal to h over p, and therefore this equals nh over p, where p is the momentum and h is the Planck constant. Angular momentum, L, is given by r times p, position times momentum. This is also equal to nh over 2 pi p multiplied by p, which cancels to nh over 2 pi, which equals nh bar, where h bar is simply just h over 2 pi. As such, the angular momentum must be quantized. Now, the importance of the correspondence principle is highlighted by the fact that Bohr did not postulate this restriction, but rather was able to deduce it by making explicit use of his correspondence principle. The entire basis of the correspondence principle, which underlies the Copenhagen interpretation, is a simple belief that classical concepts are indispensable for our understanding of physical reality. Only when we describe or match quantum phenomena to classical concepts can we hope to understand them in any sort of physical sense. The Copenhagen interpretation is also rather important in a philosophical sense. The paradigm theory of Thomas Kuhn, a famous philosopher, in which old science is jettisoned and replaced by a new science, is an idea that is subscribed to by many. Kuhn believed that scientists worked within a given framework, one that they would adhere to in order to derive knowledge. Eventually, there would be a catastrophe in which a crisis would occur and the old theory or system of obtaining knowledge would come into question. After this period, a new leading theory or paradigm would occur, and this would then be followed. However, it can be seen that in the Copenhagen interpretation, that this was not the case. Indeed, the interpretation as a key feature demonstrates the commensurability between classical and quantum theories. Bohr himself believed that his theory was simply an extension of classical physics, and that there was no change to the basis of physics being used, rather that certain aspects were restricted. The story of the development of the Copenhagen interpretation is a story of the change from the old quantum theory to a new quantum theory. This new quantum theory is seen in the work of Werner Heisenberg. The work of Heisenberg indicated a shift in the nature of quantum theory from one that was based on models to one that was based on more abstract features. It gave no direct picture of the phenomena it was describing. Many other physicists working on quantum theory had strived to interpret the theory such that some sort of physical model or physical visualization could be ascertained. However, Heisenberg's work on matrix mechanics broke away from this. The creation of Heisenberg's matrix mechanics comes from the study of optical dispersion. Classically, this is a study related to frequencies of electronic motions inside of the atom. Heisenberg decided to limit himself to looking at the frequencies of radiation. It's possible to represent these most simply in a two-dimensional array. Heisenberg then made the decision to represent other physical quantities by a similar structure of two-dimensional arrays. He was in fact able to represent the position x in such a way. Heisenberg used this basis to determine the energies of a quantum simple harmonic oscillator system. The linear harmonic oscillator has a potential energy equal to a half kx squared. We can then use the fact that omega, the frequency, is equal to the square root of k over m, where m is the mass, to get the fact that v is equal to a half m omega squared x squared. Today, we apply such things called ladder operators, which allow us to jump from the form of one energy to one above or below for the quantum harmonic oscillator. Eventually, this leads to the remarkable fact that for the harmonic oscillator, the energies come in the form of En is equal to n plus a half h bar omega. Remarkably, these are the energies that were determined by Heisenberg. Moreover, Heisenberg discovered that the ground state energy was in fact E is equal to a half h bar omega. He had discovered that the system had a lowest energy that was non-zero, and ultimately, this related to his famous uncertainty principle. The existence of a zero-point energy had been discovered a year before Heisenberg's formulation by Robert Millikan, who studied molecular band structure. Now, we have a new part of the interpretation of quantum mechanics. Firstly, Heisenberg's solution used arrays that contained complex numbers. Before this point, scientists had simply used complex numbers for convenience. However, Heisenberg's work had shown that the use of complex numbers was key in interpreting quantum mechanics in a mathematical sense. Heisenberg had noted in general that his mathematics was non-commutative. The idea of commutation is key in interpreting quantum mechanics. Two things are said to commute if AB equals BA. If not, they are said not to commute. In quantum mechanics, the commutator of two observables is described as the following. AB, in brackets, is equal to AB minus BA. It is found that if AB is equal to 0, then the two observables commute. If not, then they do not. Heisenberg's work was then continued by Born and his assistant Jordan, and they were able to use matrix mechanics to write down a matrix for momentum, P, and found that the commutator, xp, of position and momentum gave an answer of IH bar. In other words, position and momentum do not commute. This is the basis of the famous uncertainty principle, which is key to quantum mechanics, and states that we cannot simultaneously measure the position and momentum with exact precision. such that delta x delta p has to be greater than or equal to h bar over 2.